Question 21 wants first of all two differences between isotopes of the same element. So definition of isotopes, remember, is that they're atoms of the same element with different numbers of neutrons. So that's your first difference, is the different numbers of neutrons. And the consequence of that is that the mass number, which remember is the sum of the numbers of protons plus neutrons, will be different. So different mass number is the second consequence. So then we have to complete this table with the information it's given us. So for this one, we're given the proton number. Remember, the number of protons is the atomic number, and so that's the thing that gives you the connection to your periodic table. So you just say, right, 26 protons means atomic number is 26. You go to your periodic table, and element number 26 is iron. So we can put that in there. Mass number, as we said a minute ago, is protons plus neutrons. So it's 26 plus 28, which is 54. Will be the mass number for this particular isotope. That's not the same as the relative atomic mass, remember, that's an average of the mass numbers of all of the different isotopes weighted by their abundance. So that's not the same number as you get for the relative atomic mass on your table, but that's fine because this is just one particular isotope. And it tells us the charge is 0. If the charge is 0, that means you have equal numbers of positive protons and negative electrons, so 26 protons must be balanced out by 26 electrons. So that's your first row. For the second one, we have to work a little bit harder. If we start with the fact that it's 2 minus, that means you have 2 more negative electrons than you have positive protons, because an excess of 2 electrons gives you 2 extra negatives, so the overall charge is 2 minus. So that means there must be 34 protons to give you that difference. And so then again, having worked that out, you can go to your periodic table, find element number 34, because the proton number is the atomic number, and that's selenium. So that's Se. And the number of neutrons, well, that's the mass number minus the proton number. Okay, because protons plus neutrons adds up to 80. So if we take away the 34 protons from the total of 80, we get 46 neutrons to complete the table. Okay, so in part C we have to complete this diagram for an oxygen atom. So we've got the 1s subshell already filled in, so you've got to be able to complete that diagram by labelling the remaining subshells and putting the electrons in. So that's all there is in the first shell. So in the second shell we have 2s, and then we have 2p. Okay, so those are the subshell names, and you need to be able to do that all the way up, in fact, to 4p, so including the 3ds and all that complicated bit at the end. So this is a relatively simple one. And then oxygen is atomic number 8, so we have 8 electrons altogether to put in. So we've got 2 there, we can put 2 into 2s, gives us 4, and then we've got 4 electrons to distribute between these 3 orbitals in 2p, and remember that they will stay unpaired if they can, because by going into separate orbitals they will be further apart on average, therefore there's less repulsion between them. So as we fill up from our 4, we're going to go 5, 6, 7, so that would be nitrogen, with each of the electrons in a separate orbital to minimise the repulsion. But when we get to oxygen we've got 1 more, and so now we've got to pair up, and so we get that. D wants a dot and cross diagram for calcium nitride. It gives you a lot of help in this question, which you can't always rely on. It gives you the formula of calcium nitride and tells you it's an ionic compound. It might not have done either of those things. You can work out it's ionic, because that's a metal and that's a non-metal, and having decided it's ionic, you can figure out the charges on the ions and hence get the formula. So, you know, be pleased that they helped you with that, but don't rely on them always doing that. And it also prompts you, when you do the diagram, to show the charges on each iron. But again, they may not do that. So you have to remember how these dot and cross diagrams work for ionic compounds, which is that you show the positive and negative ions separately. They're not going to expect you to draw the calcium ion out 3 times and the nitrogen ion out twice. I mean, that's just a waste of time, and they realise that. So the thing to do is to say, right, I'm going to have 3 lots of the calcium ion, which is 2 plus, so you draw the bracket round it and the charge outside, and then 2 lots of the nitride ion. Remember, it's nitride because you've just got extra electrons. There's no extra oxygen, so it's not nitrate, and that's 3 minus. Because it's a group 5 element, so 3 extra electrons to take it up to 8. And then you've just got to put the electrons on. So a calcium ion, remember, it's lost its 2 outer electrons, so you just leave it showing the empty outer shell. Don't draw the next shell down. You probably would get the marks for it, but it's just a waste of time and it's kind of confusing. So the point is that it's had its outer shell emptied, so that's what you should show. The N3 minus ion has the 5 electrons that it was born with because it's in group 5, so let's put those on as crosses, and then it has 3 ions that it's gained from the calcium ions being formed, so you get 3 like that. Now part 2 is quite a lot harder, because all it tells you is that when it dissolves in water it actually reacts, it doesn't simply dissolve, and you get a mixture of 2 alkaline compounds, but it doesn't tell you what they are. So you've just got to think, what could they possibly be? We've got to do something with the calcium, and you think, well, what would the ionic compound containing calcium be? And of course, the alkaline compound containing calcium, and the obvious answer would be calcium hydroxide. And then we've got to do something with the nitrogen. What would the alkaline compound containing nitrogen be likely to be? And you're going to guess ammonia. Okay, so you can't be certain of these things, but it's just not immediately obvious what else it could possibly be to give you 2 alkaline compounds. So then you think, right, okay, those are our compounds, but obviously this needs balancing. So we've got 3 calciums, so that's going to have to be 3 calcium hydroxides. And we've got 2 nitrogens, so that's going to have to be 2 NH3. And then if we're right, we should be able to complete it just by balancing the right numbers of waters. If we're wrong, then it won't simply balance like that. So let's see what we've got. We've got 3 lots of 2 oxygens, which makes 6. So 3 2s are 6 oxygens, so that would mean that has to be 6 H2O. And then comes the crucial bit, that if this is right, the hydrogens have to balance. So we've got 6 2s are 12 hydrogens on the left. Here we've got 3 2s are 6, and 2 3s are 6, and 6 plus 6 is 12, so that balances. So that was your equation. But you can see you had to speculate a bit at the beginning, because you can't know for sure what these alkaline compounds are, but on the other hand, what else could they be, given the elements that you've got there? So it wasn't an impossible question, but it was a little bit trickier. So in part 3 it wants you to complete this little picture of calcium oxide. So calcium's in group 2, so it's Ca2+, and oxygen's in group 6, so 6 outer electrons, it will gain 2 more to give you 8, and therefore it will be 2 minus. So those are your ions, and you've just got to put those onto the diagram. And the thing to remember is that they alternate in a lattice, okay, because that's the only way you're going to maximise the attractive forces between the oppositely charged ions. So if we choose to make this one Ca2+, the ones immediately next to it, so that means this one has to be O2 minus, and that one has to be O2 minus, and this one has to be O2 minus, because those are its immediate neighbours. And then we can just do the same thing and say, right, the immediate neighbours of this one have all to be calcium, so that one is, and this one is, and this one is. And then the immediate neighbours of this calcium must all be oxide, so that one is and that one is, but this one has to be as well. And that just leaves this one, and that's obviously a calcium because it's next to these 1, 2, 3 oxide ions. So that's Ca2+. Okay, so that's your completed picture. You could do the oxides and calciums the other way around, that would be fine. Part 4 wants a dot and cross diagram for a molecule of N2O, so we're talking about covalent dot and cross this time, so overlapping circles to represent the atoms sharing electrons. And we've got to try and figure this out. Now this one's a little bit trickier actually than some of them, but if you start at this end and you think, right, what does this nitrogen need to get 8 electrons in its outer shell? And you think, well, it's in group 5, it's got 5 already, it needs to bring 3 more in. So the obvious way for it to do that is to form a triple bond. So let's do that. And then see if that works. You know, we can't be sure, but it seems reasonable. So where does that leave this nitrogen? Well, it's in group 5, it's used 3 of its outer 5 electrons to form that bond, so it will have 1 lone pair left over to account for its 5. So that's that atom settled if this model is going to work. So what about this one? So it's used 3 of its 5, so it will have 2 electrons left over. So your first thought might be, okay, that will have a lone pair as well. But the trouble with that would be that that would then already have 8 electrons in its outer shell, and because it's a period 2 element, remember period 2 elements can't go above 8. If it was in the next period down it could, and that would be a possibility, but here it's not, because then there's nothing it can do to bond to the oxygen because it hasn't got any more space in its outer shell. So it can't have those electrons as a lone pair. Nor can it share them in a normal covalent bond, because that would involve bringing in electrons from the oxygen. So again, that would take you above 8. But what it can do is this. In other words, it can form a dative covalent bond in which it donates a pair of electrons to the oxygen, like that. Because that way, this nitrogen stays with only 8 in its outer shell, so it's not breaking any rules. What about the oxygen on the end, though? Well, it already had 6 electrons, so it's going to expect to bring in 2 more to go up to 8 in its outer shell, and of course that dative covalent bond neatly achieves that. So that's actually the correct structure. So you have N, N, O, like that. If you started it differently and started at this end and said, right, let's give this oxygen a double bond and went through, you know, which is what you would normally expect, you would have ended up with this. And that's perfectly fine as well, because again, that doesn't break any of the rules. So either one of those kind of structures would have been fine.